Session 3. Today we'll start with Martin, and we'll continue in more or less the topic of, well, that's a simulator, but later we are going to go into the broader topic of compilation. I think this is a quite heavy session on that topic. Yes, so we're now listening to how we can use or derive a Kronecker-Free functional quantum simulator. I'll be interested to hear what that is and how we can do that. Thank you, Martin. Here you go.
Thank you. Yes, let's get started here. So this is really about establishing a connection between a specification of what circuits are and implementations of simulators. We are used to have these notions of circuits in the quantum communities. Just go more in detail into that in a moment. They are very declaratively written, and they can be composed in many ways, horizontally and vertically. On the other hand, we have the efficient quantum simulators that are very imperative in nature. They will usually use in-place array updates to update some global state vector. And the addressing computations are really done using complex addressing at computing based on the bit index in the number representation of the qubits and so on. And we very rarely see a connection being established. So what we will show here is that of course one thing we could do is to based on the semantics of this thing, and that's pretty well known, how you specify the unitary matrices. We'll come back to that for such a circuit. We can of course generate that huge matrix, and then the effect of applying such a circuit to a state is simply to do matrix vector multiplication, and you will get then the end result. But it turns out that there's a way to actually get rid of this huge matrix intermediate structure using a notion of something called vectorization. It's basically a connection between stacking columns and then the Kronecker product. So I won't go much into detail here. Probably in this room, pretty much everyone knows about this notion about how to model a qubit, how to model the single qubit gates, and here we have all the various gates at a single qubit level, and then here we see this how states of more qubits can then be modeled as products of these standard bases. And we see, for instance, for 4-element, for 2 qubit states we need 4 elements. For 3 qubit states we need 8 elements, and so on. It grows drastically with the number of qubits. When we want to specify the semantics of multi-qubit circuits, we basically define it in terms of the Kronecker product, the tensor product here, A times B, and then we use this block notation here. This is a usual definition, and it comes with various properties. There's a identity element here, and then we also have special matrices used for specifying qubit swapping and for specifying these so-called control gates. And they can be specified here also using block notation. We see the swap gate here, over here, and so on. So this is the foundation for specifying the semantics of circuits. And we can then write a small language, a DSL, for specifying circuits in a functional language, for instance. Here we see how different should probably use the mouse here. We see here how different circuits can be written using the base gates, syntax for those, the swap gate, which works on 2 qubits, and then we can compose circuits in sequence. That means that they're composed in this direction here, And then we can also compose them vertically by adding multiple circuits. And then we have this thing, the control gates, that will allow to create entanglement between qubits. And this is then specified with this C constructor here, and takes also a circuit as argument. It can be a control of any arbitrary circuit. So, and here's an example of how to write up in a functional language a specification of this circuit here. So we use the tensor product here, and we are explicit about where the identity is. So the first layer here, I tensor H, is I here and H here, and so on. So this is a way, and then swap is specified using these two crosses, and control gates are kind of anchored, and so on. So this is pretty useful, pretty usual. And here we see that we can then start writing some function in a functional language, maybe a host language. If it's an embedded DSL, we can start writing, for instance, a partial function here that will give the height of any circuit. And there's kind of a well-formedness condition here that when you put two circuits in sequence, the heights needs to be similar for the two circuits that you compose. But other than that, there are no side conditions. Then the semantics of a circuit can then be written up compositionally using standard matrices, unitary matrices. So we see here that the semantics of some circuit here, C, with a height K, will then be specified by this unitary matrix, which is of size 2 to the K times 2 to the K. And of course, we can compute the semantics, or the semantics of applying a circuit to some input vector by just doing matrix vector multiplication. Now the question is, can we do better than this? And of course, I should say there are many simulators around. They are not doing this unitary matrix simulation. They are really doing these updates on imperative updates on state vectors directly. So, but how do we actually go about generating or calculating an interpreter? We want to be able to write an interpreter, but we want to do it in a formal sense, starting with the property that we want. So for any circuit C such that HC equals K and some particular state vector, we want the property that the interpreter IC of V should be the same as the semantics of the calculation here, right? So the question is, how can we derive this interpreter? And this is based on this notion of vectorization and the properties of matrix multiply. Vectorization is this particular thing. One can look up in Wikipedia how that is defined and so on. There's also some a preprint which specifies some direction for where to find this mentioned in the literature. So basically, the Kronecker product can be specified by doing some kind of unvectorization here, and then specifying that results in a matrix. It needs to be compatible with B and A appropriately, and then basically vectorization is the idea that you take the matrix and you take all the columns and then you stack them on top of each other, and then that will create a vector again, one huge vector. So unvec is the opposite of that thing. So then we have some other properties here. We basically flatten, and vectorization and vector here are just the transpose of A, and then we flatten that. That's the definition of vec and unvec and so on. Then we also use this property that applying a matrix is really mapping a function that will do matrix vector multiplication over the transpose of B here. And then we use also the standard transposition properties. Now based on this, we can start calculating the interpreter. starting from the base cases here. Here we have those directly with when C is the identity, we can just return the vector unmodified. And for small gates, we'll just apply it immediately, the semantics of the gate here. For composition, we can, based on the properties and from the denotation and matrix vector multiply properties, we can simply calculate using induction how the interpreter should work on such circuits. Okay. For the tensor product, this is where we are going to use vectorization trick. It turns out that we can, based on the semantics, we can use the vectorization trick here to get this equation. Then we use properties of matrix multiply and the transposition. And I understand here, of course, it might be difficult to track the number of transpositions you're doing and so on. But if you're steady on paper, you will get the right number of transpositions. They cancel out, of course, in some cases. And then we get these. Then we can use matrix multiplication, the functionalization trick twice here to get these lead bindings, and then we can apply induction to actually call the interpreter recursively instead of generating the Kronecker product. Okay, so there's no full matrix here. This is how it looks in an interpreter. This is written up in standard ML. It could just as well be Haskell or any other functional language. So you can basically write a small interpreter here, and it will run much better than if you basically create the unitary matrix to start with. So here are some small benchmark. We are not claiming here to state that this is state-of-the-art simulator. We're just saying that this might actually give some possibilities for various kind of optimizations, and at least it's an elegant way of presenting how an interpreter. We have some students who could actually implement these things at the bachelor level, writing these kind of interpreter, and suddenly they can work on quantum algorithms that use their own interpreter, and they can actually their own simulator, and they can get sizes that are now using maybe 15 qubits instead of 7, right? So it's a little bit more interesting for the students to actually work with this, using these tricks that are quite simple to implement. So here we see different versions. So this is the red one is a standard unitary simulator, and then we can see the blue one is the one I showed on the slides, and then we can get a little bit more performance out of it if we start using these updated mutable array views, where you can actually store into, but there's still index calculations going on with all these transpositions and so on. That comes as an overhead, and we implemented some imperative version here, and then you could see that there's still something to fill the gap for kind of starting from the very functional interpreter here down to a more imperative one. But maybe in the future we can fill that gap. And to end the talk, there's a lot of related work, of course. Many simulators out there, QSIM, Quest, and so on. We had and I was giving a presentation at the array workshop where we were actually targeting a data parallel language with this approach, but where you have gate operations instead of this compositional algebraic constructs. And there we could then generate a gate library in a data parallel language, and show that we could actually get gate fusion just from the language, the host language implementation of map fusion in the language, because it's really as a map over index transformed vectors. So that was one result. There are a lot of opportunities for future work. Of course, we should do more comparisons with state-of-the-art simulators. That was not included here. We have done some work on monadic generation of circuit specialized simulators, where we we basically could generate specific data parallel code for a particular circuit using a monadic approach to code generation. We could also, using this thing, it is quite easy to identify certain things. For instance, that a tensor of many things is really the identity. But we could also see something else, that maybe a tensor of multiple gates are really symmetric. Based on that, we can do a much more efficient simulation of those things, and also anti-symmetric circuits. So this is some future work we can go into. And it's a little bit different from what you would see in traditional simulators. They are not kind of doing this thing. Offline gate fusion, of course, try to do gate fusion up front before you actually simulate, might be a good idea. Lots of stuff with measurements. There are a lot of students' projects here doing measurements and implement algorithm. And we also have some work on swapping qubits that are distant, far apart, and how that can be done efficiently from a calculation point of view. And with that, thank you.
Thank you very much, Martin. So, are there questions?
And I've been very excited to hear about questions from this community.
Hi, nice. Thanks for the talk. One question I was having was, as I was listening to the talk, was like, how are the interpreted programs? Do they look like basically like something similar to what a tensor network representation of that circuit would look like, or the operation would look like, or are they fundamentally different from what would be happening? Because it seems like the outer product formulation into those two unvec operations and the multiplication on those two axes kind of looks similar to what a tensor network would do. So. Yeah,
yes, so I think there's some relation to some work in CX calculus, for instance, these kind of tensor algebras. I've not been able to digest something simple that I could kind of easily understand, I should say. So I think some of this thing is not really that advanced, right? And I was very surprised not being able to find anyone who have done something simple like this. So that's my biggest. That was also my biggest question here to this community, because I was kind of, why did no one do this? And this idea of actually establishing a connection and being able to calculate, I think, is a neat thing. But
thanks for the talk. Very nice. Just a comment. The sort of algebraic underpinnings of the. I mean. So in fact, if one takes a more abstract view, then you have it is indeed related to the ZX calculus and the other things you mentioned, but really the structure is that of a so-called compact closed category. So you're taking what would be, because you have a closed category, you could regard morphisms as, it's this map state duality essentially. And vectorization is taking the name of a morphism, as it's called in categorical logic. So there's some quite elegant algebra that underlies exactly what you were doing. Actually, there's a little synopsis of the relevant things at the end of the paper I mentioned about the quantum monad in my talk, but I mean, it may be helpful in seeing the...
Thanks.
Yeah, thanks for the talk also from my side. So one thing that I learned when programming a quantum simulator is that there is this trade-off between the load that you put on the CPU and the load that you put on the memory. So basically you can kind of have this trade-off by like either reshaping the arrays a lot, which requires a lot of copying around, or you can like directly act on the memory, like with matrices. Maybe could you comment a bit on that? What are your views on that? Is it like more a memory-heavy simulator, or is it more a computation-heavy simulator? Or?
So thank you. So I think from the, it's definitely a more computational heavy. You could see some things are being recomputed multiple times instead of having it stored in memory. You see you map over something many times with the same circuit. So depending on also how you specify your circuit, you might have different things, different code paths being executed multiple times instead of having things being cached in memory as kind of just the unitary matrix which will then instead fill up. All right, so you have in that respect. Another thing is that, of course, for some of the more advanced simulators, QSIM, for instance, I believe, have this notion that they need to work on multiple devices and so on, where it might be very important that you actually orchestrate your qubits that are operated on together on the same device and so on, so that you minimize the number of communication and duplication of memory, because there you also need to then synchronize memory again when you have different GPUs even working on different parts of the state vector. And then, of course, you need to somehow copy those. So that will be the state-of-the-art simulators. They're doing these kind of tricks. And this, of course, this simulator we are presenting here is not at all doing these kind of things, right? I mean, this is a very simple one slide function you can write on.
Yeah, thanks, Martin. The nice thing by doing an interpreter is that you can actually step outside the circuit language. And so more modern languages in quantum computing have control flow and feed-forward of measurements and so on. So have you looked into how you would do the measurement of the register and then use that bit in a future computation?
Yeah, so we have played with various, some students have played with various ways of having constructs in the language for specifying, for instance, you do a measurement and that number of times you iterate, and then you establish a number, that number of times you use to do something. And the one thing is that to capture that in the language, in the DSL itself, so that you can actually move that DSL and move it to a GPU or something, or you could do it as a host, where you could do arbitrary computations, of course, determine whatever you want to do, whether you want to simulate different circuits or whatever based on the measurements. So there are various trade-offs. Right now we just have it at, here of course you can do measurements, and then you can you collapse the state, or you can continue on the collapse state, or you can cheat and not collapse or whatever, right? I mean, that's kind of depending on.
So one thing I would suggest maybe is to move away from DSL and to use one of the IRs that's already being used in production for a lot of systems, because it's already doing this for you.
Yeah, yeah.
Okay, thank you for the talk. I'm wondering, is your approach compatible with a different architecture of simulators, like BDD based or something like that?
I think from the DSL, I mean, it's quite easy to generate QSIM code or Quest code or whatever. The small DSL, we can, you basically just, there up front, you just need to kind of be determined on the number of qubits you're doing. And then it's just by the interpreter or the compilation will then just keep track of what qubit are you operating on, and then you can, with that information, you can generate the gate commands for particular backends.
Okay, thank you.
All right, let us thank Martin one more time.